All right, I'm going to go back over, or I guess finish going over the problem that we got cut off from in class today. So just to recap, it says, and I'll send this to you as well in the what is it called? Remind. So a manufacturer does not know the mean, so we don't know the mean. Excuse my Band-Aid. I got a blister from cleaning my bathroom. And the standard deviation. We don't know either of these. And what we do know is we are looking at a set of ball bearings from a factory, and we're looking at the diameters. So we know that we reject any ball bearing that has a diameter larger than 2.4. So we're rejecting diameters bigger than 2.4 centimeters, and we know that there are 5.5% of them that have too big, right? 2.4 centimeters is too big, so there's 5.5 of them. And then we also know that there are 8% of them, that's an 8% of them that are too small, and they have 1.8 centimeter. So because these are not equal percentages, if we were to look at a standard or a bell curve here, they're not centered around the mean. So we can't just say that they're the same distance away, and that if it was that easy, we'd be able to easily find the mean. But we don't know that. They're not the same distance away. So what we do know is over here, if they're too big, meaning it's 2.4 or larger, we do know that this percentage of them, there's 5.5%. And then over here, the ones that are too small, because they have diameters less than 1.8 centimeters, we know there's 8% of them that have that. So if I rewrite this using the notation that we are interested in using, that we use for these problems, we would say that the probability that the ball bearing is less than, right, the diameter of the ball bearing is less than 1.8 centimeters, we know that's equal to 0.08, 8%. And then the probability that the diameter of the ball bearing is bigger than 2.4 centimeters, we know that that probability percentage is 0.055. So again, in the previous problems we've worked on the past few days, we were looking for either this number along the x-axis, we call these the x values, or we were looking for a percentage. So in this case, we already have both of those. So now we don't know the mean and we don't know the standard deviation. So what we want to know is, by utilizing a standard normal curve, what it's going to tell us is how far away from the mean. So the number of standard deviations away from the mean, this probability will be, the value that produces this probability. So that's why we reformat this this normal curve onto a standard normal curve, because all of them act the same way. So in the standard normal curve, we know the mean is 0. So even though this one has a different mean, we still know 50% of the data is over here and 50% of the data is on this side of the mean. All right, and then we know that the standard deviation is 1. So we're moving up by 1 or down by 1 in that direction. So if we use the standard normal curve, we can see what z value, right? What z value, meaning how many standard deviations away this data point would be that would produce that 0.055 percentage. So we can use the inverse normal function of our calculator to tell us this value. So the inverse normal on our calculator here. So I'm going to go to my second, distribute. I'll bring this up closer to you guys, right? And I'm going to use my inverse normal. Okay, and I want my percentage to be, so the 0.055, so I guess I should have mentioned this. I don't want to use 0.055 because that's this direction, right? I want to go up to that point. So my calculator is programmed to find probabilities in a cumulative way. So what would I do? There's a few different ways. I can say 1 minus 0.055. So 1 minus 0.055, that's going to give me the other percentage. So all of this other space over here. I'm not doing the 8% just yet, but all of this other space. All right, so now I'm using 0.945 on my inverse normal. So 0.945, I'm keeping my mean 0 and my standard deviation 1. And it says the z-value that would produce, so now we're coming back over here, the z-value that would produce this percentage on the right, like greater than this z-value, would be 1.598. So that is the z-value that would produce this percentage. So here's what we do with that. If we know the z-value tells you the number of standard deviations this value is away from the mean. So I want to know whatever this data point is right here, whatever this data point is, the 2.4, I know that it's 1.598 standard deviations away from the mean. So we use the z-score formula to help us organize that information. It's x minus mu divided by sigma. So the z-score, the number of standard deviations, is 1.598. That equals my x value is 2.4. I don't know my mean. I don't know my mean, nor do I know the standard deviation of this data set. I can't use 0 and 1. That's for the normal set. So here's one equation I'm going to use. Now it has two variables in it, so I can't solve it yet. That's why we have another piece of information. So same thing, I want to know what is the z-score value, how many standard deviations below the mean would produce a 0.08 over on the left side here. So we're looking at a cumulative probability of 8% up to this value. So again, I'm going to use my inverse normal. This time I can just use 0.08 because it's cumulative and it's on the right side. So, use my calculator again, inverse normal. Now I'm going to change it to 0.08 for 8%, and I still use 0 and 1 because I'm standardizing. All right, so now we see this is negative 1.405. So it's negative because it's to the left of the mean. So it's negative to the left of the mean. So that means whatever this number is going to be 1.405 standard deviations below the mean. So 1.8 is negative 1.04 standard deviations below this mean. So I'm going to set up another equation using my z-score formula. This time, negative 1.405 equals, now my x value is 1.8 minus mu divided by sigma. I have two equations here. Those two equations are both in terms of the same variables. So that's called a system of equations. So I'm going to take these system of equations, and I'm going to solve them, right? So let me remind you how to solve a system of equations. There's three ways: graphing, eliminating, or substituting. So the first thing I'm going to do on these is I'm going to multiply both sides by sigma, okay? This is the way I'm choosing to solve it. You guys know there's multiple ways. So it's 1.598 sigma equals 2.4 minus mu. And then when I do that for the other equation, negative 1.405 sigma equals 1.8 minus mu. So I'm going to choose to solve this using elimination. You may choose to solve this using substitution, where you solve for one of the variables. So I'm going to subtract the second equation from the first. So hopefully you see why I'm going to do that, but if you don't, it'll be very clear in a second. So 1.598, I could probably try to subtract this. I'm subtracting a negative in my head, but I think we all saw today that my brain is not quite working. So I'm rounding these values, so I rounded here, so I'm going to have to keep rounding. It's pretty awful. But anyways, so 2.4 minus 1.8, why can't I do that in my head? Who knows? So negative mu minus negative mu, so negative plus a positive mu turns into 0. So now I have this equation, 3.003 times sigma equals 0.6 if I'm solving for sigma. Divide both sides. So 6.6 divided by 3.003. So that gives me a sigma, a standard deviation for this data set of 0.1 0.1998. And that is it for sigma. So really, if I was using IB here, IB rounding, I would really just round this to 0.2 because you know we want 3. So anyways, okay. So if this is sigma, then mu, I would just solve by substituting this back in. So 1.598 times that number, and then I'm going to say 2.4 minus that answer. So I got a, oh man, I typed in 2.1. Anyways, I know what this answer is supposed to be. It's about 2.08 because I worked it out earlier. So that may be off a little bit. I typed 2.1 into my calculator and I'm too lazy to go back and do it. But so this is how we could find the what are the words? Average and standard deviation by utilizing the standard normal curve. So I'm going to try one more example for you guys. So let's say it's known that the average height of 6-year-old boys is 105 centimeters, and 22% of the boys are taller than 110. Okay, so find the standard deviation of the height. So we're finding the standard deviation, and I know that the probability that a height of a boy is taller than 110 centimeters is 0.22. It's 22%. All right? So we are assuming that these heights are normally distributed, right? The heights are normally distributed with an average of 105 and our sigma squared. All right. So again, this is a situation where if we think of this normal curve, we know what this one is where the average is, 105. And 110 centimeters is over here, and we're taller than 110. So all of this area is 0.22%. So again, we have our x value, we have our percentage. So we're look to find a sigma. Anytime you're asked to find a sigma or a mu, you should be standardizing your variables. So I want to know if I were to retrofit this onto a standard normal distribution, I would want to find the z value on the standard normal distribution that applies to this number. So again, if I were to look at standard normal, here's 0, I want to know what is the z value that has a 0.22% over here. So again, that's where I do 1 minus 0.22 because I know my calculator is programmed in a cumulative way. So all of this other area is 0.78, right? All of this. So I would use my inverse normal, where the area is 0.78, average is 0, and standard deviation is 1, of course.
Teachers who placed an order for a no toys for Hay shirt can pick up in Ms. Moore's office after school today, room 503.
All right, so when I did that, my inverse normal, just by typing this in, again, I'm using 0.78 because I'm going up to this z value. That was 0.772. So I'm going to now use the equation of a z-score. So
bus riders are always 100, 200, 300, 900, and cottages 1 through 4 may be dismissed.
all right, so I know that whatever this number is, so up here it's 110, to produce the 22% over to the right of it, it has to have a z-score of 0.772. It's 0.772 standard deviations away from the mean. All right, so I know 0.772 equals 110 minus 105 divided by sigma. So now I'm just solving for sigma. And when I do that, I get a sigma of 6.48 centimeters. So that's the standard deviation of this particular data set. So I encourage you to make a sketch, and I really think it's helpful just to organize information. So you will always need to standardize your variable using a z-score when you are looking for either the standard deviation of a data set or the average, or like we saw in the previous example, maybe you need both. Okay, so if you need more help on this, if you're working over the break, I'd be more than happy to meet with you guys, depending on the day, obviously, and we can go over it. So remember not next week, but when we come back from Thanksgiving, we have one review day and then a test day. All right, happy Thanksgiving!
That's why there's